Hey guys, this is for our class for Wednesday, the 14th, and also my Tuesday, Thursday class on the 15th. So the 3 lessons you need to do, hopefully by the end of the weekend, are 3.1a, 7.1, and 7.2. So our last class, we talked about the properties of exponents. So this is a great reminder. If you have this sheet, maybe you could just, if you don't print all of the slides, maybe you could just print this one just to have these rules in front of you as you go through these problems. So just a quick reminder about the exponent of 0. So a lot of people, the common mistake would be that, okay, well, 6s is being raised to the power of 0, which would be equal to 1, but that is actually not correct, right? Because 6 is being multiplied by s to the 0 power. Well, s to the 0 power is 1, but 6 times 1 is 6. So make sure you do not make that mistake. That's a very common mistake. So I just wanted to point that out to you. All right, so anytime you have a negative number raised to an even exponent, you're going to end up with a positive answer if it's written in parentheses, like the first one here, this first example. So we would multiply -4 together 4 times. Well, every time you have 2 negative numbers, when you multiply them, you get a positive answer, right? So when you have 4 negative numbers, same thing. Negative times a negative is a positive. Negative times a negative is a positive. So your final answer would be 256. However, the second problem is basically saying what is 4 times 4? But then you're finding the opposite of that. And when you're putting these in the calculator, you want to be very specific as well. So if you have a problem like the first one, make sure you put it in your calculator exactly like you see it. If you drop these parentheses and you put -4 to the 4th power in your calculator without parentheses, it's going to tell you the answer is -256, which is not true, right? So just be careful when you're using your calculator. Always try to type exactly what you see. All right, and then this problem number 3, or the third one, I should say. All right, so just remember, the rule for division is to subtract. So 7 minus 11, the difference in 7 and 11 is 4, but literally 7 minus 11 is -4, right? So if you subtract, that's correct, but this would not be considered simplified until you have a positive exponent. So the only way to make that exponent positive is to drop it down in the denominator. Or just think, okay, what's the difference of 7 and 11? The answer is 4. And then ask yourself, are there more 3's in the denominator or in the numerator? Since there were more 3's in the denominator, that's where our 3 ends up, okay? Of course, you can simplify this further because 3 to the 4th power is 81. So this is really 1 over 81 is the best answer. And then this is just a quick review on, once again, this isn't considered simplified. You want to make your exponents positive. The only way to make them positive is to make them go over that line. Remember, over the line, change the sign. So we would rewrite this as 2 times 2 to the 3rd power, which is 2 to the 4th power, which is, 2 to the 4th power is 16. So that would be the final answer. Of course, if you put this original problem right in your calculator, it would give you 16 immediately. So use your calculator when you can, absolutely. All right, here's problems with negative exponents. We want to make them positive. So we're going to take just the n and move it, not 3n, it's just the n we're going to move up. So we would have 1 times n to the 5th is n to the 5th over 3. The 3 stays where it is because the 3 has a positive exponent of 1. All right, so now we have a power times a power, power raised to a power. You're going to multiply those exponents. So 5 times -3 is -15. So currently that would be sitting in the numerator. We want it to be a positive 15, so we're going to bring it down to the denominator. You can't have a blank in the top, so you have to put a 1 up there. And then here we have power raised to a power, so we're multiplying -3 times -5 is positive 15, and that's our final answer. All right, on this one, we're going to bring that z to the top. So we would have z to the 3rd times n to the 3rd times z to the 6th. So it's like a -3, doesn't it? Over n to the 11th. All right, we want to get those z's together. So we're going to add 6 plus 3, and we get z to the 9th. We want to simplify these n's. So we're going to find the difference in 3 and 11, which is 8. And now, are there more n's in the numerator or denominator? Since the numerator, that's where our n stays. And that's the final answer. We don't have any negative exponents, and we don't have variables on the numerator and the denominator, so we're good. Or the same, I should say. We don't have the same variable in the numerator and denominator. All right, on this one, we're going to multiply every exponent by 2. And remember, there's an invisible 1 right here, so we're going to have 3 squared times x to the 6th, and then y to the -4th, and then we want to get rid of that negative exponent, and then we can also square 3, which is 9. So we'd have 9x to the 6th and bring our y to the numerator, and that's our final answer. All right, let's multiply everything by -1. So we have 4 to the -1st times x to the -6 times -1 is +6. So that 4 is going to jump down to the denominator, and it's 4 to the +1st, which is 4. And then when you have two numbers that have the same base that are being multiplied, you're going to add those exponents, and we get y to the 14th. I think I said 14. All right, so 7.1 exponential functions and their graphs. To determine their graphs, use test points to do a rough sketch of the graph. To solve elementary exponential equations, we're going to isolate the exponential on one side of the equal sign. Rewrite both sides to have the same base and equate the powers and solve. All right, what does that mean? Let's look. So probably the easiest thing to do when you're trying to graph these is just create you a little t-chart. And on these t-charts, these x's have already been filled out for us. You can always sketch your own t-chart. I would try to use a negative number, 0, and a positive number anytime you're making your own t-chart. All right, so we're not going to do all of these, but let's do, what if x is -2? So 2 to the -2nd, I would write as 1 over 2 squared, which is 1/4. So when x is -2, y is 0.25, right? 0.25. Oops. 0.25, and that's a positive number. All right, what about when x is -1? Well, 2 to the -1 is 1/2. 2 to the 0 power, anything to the 0 power is 1. And then 2 to the 1st power is 2, and 2 squared is 4. All right, so if we graph these as they were coordinates or ordered pairs, we go left 2, up 1/4, left 1, up 1/2, 0, 1, 1, 2, and 2, 4. So we're going to get this curvy little exponential graph, just like that. Okie dokie. All right, now this one over here, we have 1/3. So we're going to use the same x values. So 1/3 to, oops, 1/3 to the -2. So guys, just, we can put that right in our calculator, right? We're going to do 1 over 3 raised to the -2nd, and we get 9. 1/3 raised to the -1st, we bring that 3 up to the top. 1/3 to the 0, anything to the 0 power is 1. 1/3 to the first power is 1/3. And 1/3 squared would be 1/9. All right, so we would go left 2 up 9. Then we would go left 1 up 3, 0, 1, 1, 1/3, and 2, 1/9. Gonna get really, really, really close to the x-axis, but it'll never touch it. Ooh. And there we go. So those are what your graphs are going to look like when you have, you know, a base without any plus and minus, with just an x. You're always going to get these two pictures. Either you're going to get when you have a number greater than 1, you're going to have what they call a growth module. It's going to go up and to the right. Or if this number is less than 1, you're going to have what they call a decay, and that will go down and to the right. Okay, so we'll see that pattern as we go through. All right, so like I said, we could just sketch a T-chart. So let's do -2, 0, and +2. And we're just going to put that right in our calculator. And of course, guess what you can use? You can use Desmos, and it will graph these for you, which is an awesome, awesome tool. All right, I got 13/4, and I'm going to convert that to a decimal because it's easier for me to graph. So this is about 3.25. So when x is 0, anything to the 0 power is 1, and 1 plus 3 is 4. And then 2 squared is 4, and 4 plus 3 is 7. So -2, and then 3.25, 0, 4, and 2, 7. So basically, that's what we got. All righty. Do we have another one on this page? Nope. All right, here we have, we can think of this as our base graph, and then we're going to see what happens when we add 4 to our power. All right, so we'll do our 2 T-charts down here. We'll do -2, 0, +2 on both of them, and see how these two graphs compare. So 2 to the -2nd would be 1/4. 2 to the 0 power is 1, and 2 squared is 4. So if we go left 2, up 1/4, 0, 1, and 2, 4. This is our original or our base function. And then let's use a different color to do the second one. So we're just going to use our calculator. So 2 raised to the -2nd plus 4, because that 4 is in the exponent. It's up there in the power. All right, and then we're going to do 2 raised to the 0 plus 4, which is 16. And then 2 raised to the 2 plus 4 is 6, which is 64. All right, so let's see what this one looks like. We would go left 2, up 4. And then we have 0, 16 way up here, and then way up there. So basically, we're going to have the same type design, right? But it's been shifted up 4 units. You see that? No more than 4 because we went from 0, 1 to 0, 16. All right, so they should look the same. They should look the same. And we could figure out the patterns, or you know what? Just use Desmos. Why wouldn't you? Why wouldn't you use Desmos? All right, so let's do 0, -2, 0, and +2. Now this time, you notice we have a negative. So remember, these are separated, right? So basically, when it's multiplied by a -1, which is what this graph is being multiplied by, is going to flip it. It's going to be a reflection over, what do you think, the X or Y axis? Well, let's find out. Well, 2 to the -2 is 1/4, but then it's going to be -1/4. 2 to the 0 power is 1, but then it's going to be -1, the opposite of 1. And then finally, 2 raised to the 2nd power is 4, and then it's going to be the opposite of 4, which is -4. So -2, -1/4, 0, -1, and 2, -4. So it's a reflection of the original, or the base function, but it's a reflection over the x-axis. And you don't have to really remember the transformations because you can use Desmos, okay? All right, one more. You guys try these on your own, okay? So if you printed off these, you have your graph right in front of you. So go ahead and make your own T-charts or use Desmos. And let's see what you got. All right, so we're going to use -2, 0, and +2 on both of them. So 1/2 to the -2nd, 1/2 to the -2nd is 4. Anything to the 0 power is 1. And then 1/2 to the 2nd power is 1/4. And then on this one, let's change colors again. Oh, well, let me graph the first one. So we have -2, 4, 0, 1, and then 2, 1/4. So here we go, right here. So the second one's going to look like the first one, but it's going to be transformed. It's going to be a little transformation. All right, so -2 plus 3 is 1, right? So 1/2 to the first power is 1/2. 1/2 to the 0 plus 3. 0 plus 3 is 0. So 1/2 to the 3rd power is an 8. And 1/2 to the 5th power, what would that be? 1/2 to the power of 5 would be 1/32. These are tiny little numbers, aren't they? So -2, 1/2. 0, 1/8, and 2, wow, that's really tiny, isn't it? But we still get the same type graph, but it's been transformed because of that +3. All right. Now, on these, you are going to have several of these on Hawks and probably NIOPA Math as well, where you are given a function and you have to pick out which graph it goes with. So the easiest thing for you to do is just probably use Desmos. You always want to see what what Y is when X is 0. And then, like I said, I would continue with the pattern of using -2 and +2. So 3 to the -2nd would be 1/9. 3 to the 0 power is 1, and 3 squared is 9. So I'm looking for -2, 1/9, 0, 1. So this point, excuse me, this point right here can help me eliminate this one because it doesn't go through, +1. 0, 1 is right here, so this one is out. So all I needed to do is focus on these two, correct? Well, this shows me that when x is 2, y is 9. So that's going to be way up here somewhere. So it's got to be this graph right here. And this number right here is greater than 1, so it's got to be growth. It's got to be going up and to the right. This one would show decay, which means this number would have to be less than 1. All right, another one, we can either throw that right into Desmos. I'm going to use numbers bigger than, maybe I'll do 4, -4, 0, and +4. So we're going to use those calculators. 7/4 raised to the -4 minus 4 is -8. So that's a really small number, 0.11. All right, what about 7/4 raised to the 0 minus 4 is -4. That's also a very small number, 0.10. Oh, this is 0.11, sorry. So this one's bigger than the first one. And then we have 4 minus 4 is 0. So anything to the 0 power is 1, right? So 4, 1, that one's really going to help me out this time because 4, 1 would be here. This one's eliminated. 4, 1, this one's eliminated. 4, 1, this one's eliminated, which means this is the only possible graph it could be. All right, so you want to look for a good coordinate that can either make this, we don't want to make it harder, do we? We want to always make them easier, as easy as we can on ourselves. All right, let's try this one. Let's see, what do I want to use? We'll definitely use 0. Let's do the 4s again because they have those marked. So we'll do -4, 0, and 4. All right, so 1 minus a -4. 1 minus a -4 is 5. So we're going to do 2/5 raised to the 5th power. Oops. I didn't put it in as an exponent. Y'all be careful on that. To the 5th power. And I get a tiny little number. 0, 1, and then when x is 0, so 1 minus 0 is 1, so this is 2/5 or 0.4. And then when x is 4, 1 minus 4 is -3, so we're going to do 2/5 to the -3rd. And we get 15.625. So when x is 4, y is a big number, goes up, 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 right? So we're looking for 0.4, so 0.4, 0.4, this one's out, 0.4, and 0.4. So it's either this one, or this one. And then, ooh, this is going to be hard. All right, here, look at this one. 4, this crosses right here, somewhere in here. Is this going to be 15? No, this is going to be between 4 and 8. This is probably around 6, right? So these are very similar, but because this is such a big number, we know that when x is 4, y has to be way up here somewhere. So it's got to be this one. Got to be that one. And this one's definitely not it because this is getting closer to 0 when x is 4. All right, so y'all just gonna have to play around with those, use your calculator, use Desmos. All right, so I'm not gonna take the time to do this because like I said, create a T-chart, put it into Desmos, but I think you guys get it. All right, guys, so when you come to problems like these, when you notice that the bases are the same, so this is telling you that these two numbers are equal, right? Well, that means since the 2's are the same, that means that these must be equal to each other. So we're going to drop those bases. We don't need them to figure out what x is. So we're going to bring down x plus 3 is equal to 2x minus 1. Then we're going to solve for x, which means we have to get our x's together. So we're going to cancel out the smallest x. So this is gone. We have 3 is equal to 2x minus 1x is 1x minus 1. We want x by itself, which means we're going to add 1 to both sides. So the final answer is x is equal to 4. So if we play that back in, 4 plus 3 is 7. 2 times 4 is 8, and 8 minus 1 is 7. So 2 to the 7th is equal to 2 to the 7th. Well, that makes sense. So that's what our goal is. We always want to make those bases equal. So in this problem, they're not equal. However, you think about your powers, you think about what number. Can I make 8? Can I rewrite it so that I have a base of 2? Well, if you say 2 to the first is 2, 2 squared is 4, and isn't 2 cubed 8? It is. So we're going to rewrite 8 to be 2 to the third. This one already has a base of 2. And now, since we have both bases the same, we get to drop them like we did in the first problem. We're going to say x plus 3 is equal to 3. So then I want to solve for x, which means I'm going to subtract 3 from both sides. So x is equal to 0. Does that make sense? If x is 0, 2 to the third, isn't 2 to the third equal to 8? I'm sorry, you guys, I'm getting a phone call. Sorry about that. So that is correct. That makes sense. All right, so on this one, we want to make sure we get that base number that has our variable on one side of the equal sign by itself. So we're going to move minus 27. So we're going to move it to the other side. So we have 3 to the x power is equal to 27. So we want our bases to be the same, or in this case, since 3 to the 0 power is equal to 27, think about your 3's. 3 to the first power is 3, 3 squared is 9, 3 to the third power is 27. So 3 to the third power is equal to 27. That's true, which means that x is equal to 3. Okay, you got to kind of think of your powers in this way when you're trying to change those bases. All right, let's look at this one. 1/3. Is there any way to make 1/9? Can we rewrite it as a third? Well, let's see. 1/3 to the first power is 1/3, right? 1/3 squared would be 1 squared over 3 squared, which equals, guess what? 1/9. So I would rewrite 1/9 as 1/3 squared, and now I need times 5. Right? 1/3 squared is 1/9, and this says 1/9 to the 5th power. So I'm going to have to multiply those powers. So now that my bases are the same, so I would bring this down. Now that my bases are the same, I get to drop them. So I'm going to bring down 5x plus 1 is equal to 2 times 5 is 10. And now I'm going to solve for x by moving plus 1. So I'm going to subtract 1 from both sides. So I'd have 5x equals 9. The opposite of times 5 is divided by 5. And so x is equal to 9/5. X is equal to 9/5. And if I wanted to triple check, I could put that in my calculator. I could put 5 times 9/5 plus 1, figure out what that equals, and then I want to put in my calculator 1/9 to the 5th power. And I bet you $1,000,000 those two numbers are the same. So I challenge you to check those. Oh, I got another problem. Let me erase all this stuff. Oh, and that was my hint that 1/9 is equal to 1/3 raised to the 2nd power, which is what we did to this right here. All right, let's look at this one. All right, so we want our bases to be the same. Now, if I think about the powers of 16, 16 to the 1st power is 16, and 16 squared is definitely not 32, right? It's way too big. It's 256. So that tells me that I can't use 16. I couldn't use a base of 16. So if I think about the powers of 2, this would be 4. 2 to the 3rd power is 8. What about 2 to the 4th power? 2 to the 4th power is 16. And then what about 2 to the 5th power? 2 to the 5th power is 32. Which means I can change the bases to a 2, right? So 2 to the 5th power, so I'm just rewriting 32 only, I'm ignoring this for a minute. So 32 is 2 to the 5th power. So now these are equal, right? But then I would have to multiply -5 times -x is equal to 16 is 2 to the 4th power, okay? So now that those bases are the same, I get to drop them, but I do have to multiply 5 times -x is -5x is equal to 4. Oh, and this was my hint to myself when I was working these out earlier. All right, so anyway, that's not a separate problem. It's basically part of our solution. All right, so now I'm going to bring this down here. So -5x is equal to 4. I want to solve for x. The only way to do that is get rid of times -5. So I'm dividing both sides by -5. So that means x is equal to -4/5, -4/5. That's what x is equal to. All right, another one. Let's see. I know that I can write 100 as a power of 10, right? So 10 to the 1st power is 10. 10 squared is 100. There we go. So that's what 100 equals. It's 10 squared. So 100 equals 10 squared. But now I have to remember that 100 is being raised to the -x power. And then I could bring this down, 5x minus 2. And so now that my bases match, I get to drop them. So 2 times -x is -2x is equal to 5x minus 2. I want my x's together. I'm going to move, well, normally I'd move the smallest one, but then that would make this side 0. So I'm going to actually get rid of positive 5x. So -2x combined with -5x is -7x is equal to -2. So I'm going to divide both sides by -7. Negative divided by negative is a +2/7. And that's what x equals. You can always go back, plug this in for x into the original problems and check your answers. I encourage you to. All right, you guys, why don't you pause the video and try these on your own? I'm going to go ahead and solve them. but I want you guys to try them on your own and see which ones you get right, because the more you practice, the better you are going to be at these. All right, so our goal is to make the bases the same, right? So can I write 4 as 2 to a power? Yes, I can, because 4 is the same thing as 2 squared, isn't it? So 2 raised to the x plus 2 is equal to 4 is 2 squared. That's 4 times x. So those bases are the same. So I'm going to write x plus 2 is equal to 2 times x is 2x. I want to bring my x over. So 2 is equal to 2x minus 1x is 1x. So that's my answer. So if I plug this in, 2 plus 2 is 4. So 2 to the 4th power is equal to 4 squared. And both of those have an answer of 16, so I know I'm right. All right, so can we rewrite 3 to have a base of 1/3? Well, let's try it. 1/3 raised to the first power is 1/3. But would there be any way to flip that? Could I get 3 up to the top? Yep, this one's tricky, you guys, because if I raise it to the power of -1, that would equal 1 to the -1st over 3 to the -1st. Well, guess what 3 to the -1st is? We'd bring that up to the top, and it's 3. So 3 is equal to 1/3 raised to the power of -1. Right? And so what would happen if I put 3 to the -1st in my calculator? I get 1/3. So guess what x equals? X is equal to -1. Because 3 to the -1st is 1/3. I know y'all are a little confused. All right, I'm going to get rid of all this stuff. Well, I shouldn't say that. I don't know that y'all are all confused. That was not cool of me to say. All right, so on this one, we want to get this by itself on one side of the equal sign. The first thing we're going to do is get rid of the 8. So we're going to rewrite it through 32 to the x power is equal to 8. All right, well, could I make 32 equal to a number that has a base of 8? No, I can't, because 8 squared, I know, is 64. So let's think of another number. What about 2's? Didn't we say earlier that 2 to the 3rd power is 8? And I know that 2 to the 5th power is 32. Remember when we listed those earlier? So that's what we're going to write. So this is going to be equal to 2 to the 3rd power. And 32 is equal to 2 to the 5th power. But then we're going to multiply that 5 times x. So now 5 times x is 5x equals 3. So to solve for x, I divide both sides by 5. X is equal to 3/5. And that's what x is equal to. All right, 2 more, you guys. How you doing? So this is already on one side by itself. So we're good there. And then we can think of, once again, 2. So 2 is going to be very popular, isn't it? So we already know that 2 squared is 4. We know that 2 to the 3rd power is 8 because we just did that one. What about 2 to the 4th power? Isn't 2 to the 4th power 16? It sure is. So we are changing 16 to be 2 to the 4th power. But then we got to multiply -4 times -x. And we're rewriting 4 as 2 squared. So since my bases match now, I can drop them. So I have 4 times -x is -4x equals 2. I want to solve for x by dividing both sides by -4. So 2 over -4 is the same thing as -1/2. And that's what x equals. One more, you guys. So, let's see. So you always want to look at the ones that have the bigger numbers. I want to change this one. Well, 2 and 3 are going to work, aren't they? So 2/3. Well, I know that 2 to the third power is 8, so let's try this. So 2 to the third over 3 to the third. Well, 2 times 2 times 2 is 8, and 3 times 3 times 3 is 27. So 8 over 27 can be rewritten as 2/3 raised to the third power, right? That's right. And then I would have to multiply this times 3. So since now our bases are the same, this is rewritten as 2/3. I'm going to drop those bases and I'm going to write 3x plus 3 is equal to 3 times 3 is 9. I want to solve for x, so I'm going to subtract 3 from both sides. So I have 3x equals 6. And when I divide everything by 3, I get x is equal to 2. And we're done, yay! All right, now we're moving on to applications of exponential functions. Now, the good thing about these problems is that we have formulas. I love formulas. Formula tells us exactly what to do. So you definitely are gonna want to write down these formulas and keep them in front of you. I'm just writing them myself in case I don't have them on each slide. So the first one is about compound interest. We always want to put our money in compound interest accounts, right? Make money on your money. And then another one that is new this semester, we haven't done before, is continuously compounding interest, which sounds phenomenal. I'm sure I don't have my money in a continuously compounding account. But anyway, here we go. Now the first one, the population of a certain inner city area is estimated to be declining according to the model blah 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 blah, where t is the number of years. Now this one, guys, is actually very easy because you just all you're doing is substituting 4 for t, which represents time. That's what it says. Years from the present. Well, in 4 years, t will be 4. So guess what? You are simply using your calculator. Now, a brand new symbol we haven't seen before is E, which means a natural E, which is kind of like pi. It's a set number. It's already predetermined. And guess what? It's plugged into your calculator. So in my calculator, I am looking at the LN button. And on top of the LN button, I see e to the x. Do you see that? Which means the way to use this button is I have to use the second button. And then I'm going to hit LN, which actually I am engaging the natural E function. Okay, so let's try it. So in this problem, all we're doing is plugging into our calculators exactly what we see in our formula. We're plugging in 577,000. Now, we're going to hit that second button, the LN button, and on your calculator, you should see an E, and the exponent is flashing. So hopefully you see that. If not, I'll help you in class. So now we're plugging in negative 0.022 times 4. So like I said, this goes right in your calculator. So the population, we're talking about number of people. So since we have a population, we're talking about people, you always want to round to the nearest person. We don't want to say we have 0.2 part of a person, because that's just, we don't talk like that, right? So you always round to the nearest person or nearest whole number. So this is what I got. So if you didn't get that, try your calculator again. And I bet you'll get it. I bet you'll get it. All right, here's another formula. It tells us exactly what to do. It models the rise in the cost of a product that has the cost of C to the 0 today, subject to an average yearly inflation rate of R for T years if the annual rate of inflation over the next 11 years. There's our time, and there's our rate. Now make sure you always change rate to decimals. Always, always, always. So you're going to move that decimal 2 places to the left. 2 places to the left, our rate is going to be 0.035 because we moved it 2 places to the left. All right, now this is our big number. That's going to be C to the 0, or it's not C to the 0. It's, I can't even remember how to pronounce it, but anyway, that's going to be your big number right there. Okay, it's going to be the first number. So we're just going to plug this in to our calculators like we see it. So I'm going to type in 33,700. I'm going to do my parentheses, 1 plus 0.035 as a decimal. Now I'm using my exponent button, and our time is 11 equals, and it tells me exactly what the answer is, and it does tell you how to round. If you don't round right and you put in the wrong tenths place in Hawks, and my open math is going to count the whole thing wrong. So I have 979. Well, I'm rounding to 2 decimal places. That 9 turns my 7 into an 8. So I have to be careful that I plug in exactly the right number, 0.98. And that's the only answer Hawks will accept. All right, so the population of a certain inner city area is estimated to be declining according to the module. What does this module predict the population will be in 6 years? So there's our time. So T is 6. So we're just plugging that straight in our calculator, 586,000. We need that natural E, so we're doing our second button, the LN button, right underneath our log button, above our pi button. And now I'm doing negative 0.023 times 6. And I get 510,460, and we're going to round to the nearest person, nearest whole number, and that's the answer. Hopefully you get the same thing. All right, now this one seems so confusing, so I went ahead and typed out the solutions for you so that when you're doing these in Hawks, you can look exactly at this problem. Okay, you will get this problem, I promise you. I mean, probably a little, you're going to have a different element and probably different seconds. But when we're talking about the half-life, this is what you're going to use. Okay, so here is the formula, but it's very confusing the way it's written. So I'm just making this as simple as I possibly can. When it's using the half-life and they want T to equal 0, guys, this is what you're going to do. Half-life, you're going to type in parentheses 1/2. You're going to, in parentheses, 1/2 or either 0.5, same thing. And then you're going to put it to the power of, we're going to do our caret button, and then we're going to do a fraction. In your exponent, you're going to make a fraction, and you're going to put 1 over however many seconds the half-life is, okay? So in this case, it's 38, and then I got this number. And when it says round to 6 decimal places, it's very serious. You need to round correctly to 6 decimal places. Make sure you look at the number past that last digit and see if it needs to stay a 5 or if it was a 4. In this case, the 4 rounded up to a 5. Now you're going to have to do step 1 to use that answer and plug into steps 2 and 3. Okay, because 2 and 3 are about the same element that has the same half-life. So if you don't get this first one right, there's no way you'll get the other 2 right. So now we're going to use that formula for steps 2 and 3. So now we're going to plug in our sample. How much of our element do we have? That's how much it is, 11. We're going to use our answer from step 1. And this time we're changing our half-life to not a fraction, but we're using the whole number, 92. So I'm multiplying 11 times that big number, raised to the 92nd power, and I got 2.05, rounding correctly, 4. So make sure you got that as well. And then step 3, same element, same amount of grams, but this time it's asking us after 6 seconds how much of this element would remain. So we're going to do 11 times 0.981925 raised to the power of 6, and 3 decimal places, 9.85. Now I have 96. So what does a 6 do to a 9? It turns it to a 10. Carry the 1. So my answer is 9.860. You have to be careful on rounding, like I said. So let my solutions here help you with these problems, okay? Anyway, that's all I'm going to say about that. All right. Now on this one, we are talking about compound interest. Oh, we're talking about yearly inflation rates. So basically what you're going to do is, it says if the average annual rate of inflation over the next 12 years is assumed to be what will the inflation adjusted cost of a 223 bicycle be in 12 years? All right, so basically we are plugging that information straight into this formula. So our biggest number is always C sub 0. So 223. 1 plus that rate must be in decimal form. So 0.025, and our time is 12. So I like these problems. It tells you everything you need. 223 parentheses 1 plus 0.025 raised to the 12th power, and rounded to 2 decimal places is 0.91. So I know you got that too. I hope you did. All right, so here is our compound interest formula. So this one wants us to which account would pay Blanche more interest? All right, so we're comparing 2 different accounts. So we need to figure out okay, one of them compounds daily. Ooh, this is account number 2. And the first one compounds semi-annually. Let me use blue. Semi-annually at a rate of 3.7. So this is what we're comparing. Okay, so semi-annually at 3.7. And the other one is compounds daily at 3.9. Oh, and it's asking which account would pay more after 5.5 years. Okay, so there's our time. Now, the reason you have to know how often it compounds is because in this formula, the N represents a number of times it compounds per year. Okay? So for example, here's our big number. This is how much we put in. Blanche is putting in or depositing at $7,900. We're going to plug in 1 plus our rate is 0.037. That's our rate. So 0.037, The number of times it compounds yearly. Well, if it's a semi-annual, that means semi-annual means twice a year. Twice per year. You have to know that part. How many times it compounds yearly? Well, 2. And then this is that same number of times it compounds yearly times how long you're going to put it in that account. So we're going to multiply 2 times 5.5. All right. Ooh, that should be a decimal. You're going to plug that directly in your calculator, exactly like I wrote it. All right. What about the second one, the second account? Same amount being deposited. And then 1 plus our rate, this time it's 0.039 over daily, guys. How many days are in a year? If it compounds daily, it's going to be 365. We're not talking about leap year. So then we're going to multiply 365 times 5.5. The question is, which one's going to have more interest after 5.5 years, okay? So we're going to plug those amounts directly into our calculator. 7,900 times 1 plus, make a fraction, 0.037 over 2, end parentheses, raised to the 2 times 5.5. And it tells us we'll have $9,664.92 at the end of the 5.5 years. And then the other one is 7,900 times 1 plus fraction 0.039 over 365, end your parentheses. I just messed up the whole thing, 0.039 over 365. Make sure you write arrow and then raise to the 365 times 5.5. This one is going to have $9,789.90. So which one has more money? This one. That's it. That's the answer. So you'll have several of those. All right, once again, you have 2. Oh, is that the same problem? Oh, no, it's not the same problem because this one is now compounding quarterly at this rate for account 1. And the other one is semi-annually at this rate. Okay, now the first question on this one is which account would pay Maria more interest? All right, so let's do account 1 is quarterly at 0.038. The second one is semi-annually at 0.055. Now, the first question, and this is what you'll see on Hawks, it says, which account would pay her more interest? So it doesn't give us a time on step 1. So we're just going to use after 1 year. We're going to assume after 1 year. So for example, I'm going to use that formula. I'm going to put $7,800 in the bank times 1 plus our rate is 0.038 over quarterly, guys. How many quarters are in a year? Or how many quarters are in a dollar? 4, right? And then remember that rate times time. Well, I'm sorry, our number of times it compounds times time. Well, to answer the first question, we're just gonna leave our time as 1, which is just 4, isn't it? And then the second one, we're putting down the same amount of money, 1 plus 0.055. Once again, semi-annually is twice. And then we're going to leave our time as 1, so 2 times 1. So that's how you're going to set up those. You're going to figure out after 1 year which one has more interest. And then whichever answer it is, then you go on to step 2. Oh, actually, this one tells us account 2. How much would Maria's balance be from account 2 over 2.6 years? So this time that 1 isn't a 1 anymore, it's a 2.6. Okay, so that's how you're going to do that one. All right, I just want to do one more problem with you. And then we're going to cut. I don't have any idea how long this video is, but I know it's really long. The only other problem you'll see is when you have a problem that compounds continuously. And that's where this problem, right, or this formula right here will help you. Okay, compounds continuously. So you're going to put, that's your big number, $10,000. You're using your natural E on your calculator. You're multiplying, or excuse me, your exponent is going to be your rate as a decimal times time, 3.5. So this is our exponent, 0.45 times 3.5. All of that is your exponent. We're using our calculators. We're doing 10,000 second ln. We see our natural E, 0.045 times 3.5. And the answer is $11,705.81. That's how much would be in the account after 3.5 years. All right, guys, I know this is a lot. I know it is, but come to class. I'll help you. Ask me any questions, and we will get it done, you guys. All right, I'll see you guys later. Have a good day.